Well, good afternoon, everyone, both online and at Oxford. It's spring break here at the George Washington University, with many faculty and students out of station. And since daylight is being saved earlier on this side of the Atlantic, today's event is an hour later on this side. In deference to our friends in Oxford, we let you have exactly the same time for your event. Indeed, Save Daylight is in full force here in DC, revealing more clearly the effects of our government on international development, human security, and well-being. Today's event is the sixth and final installment of our seminar on multidimensional poverty, a collaboration between the Oxford Poverty and Human Development Initiative, or OPHI, in Oxford, UK, and the Institute for International Economic Policy, or IIEP, in Washington, D.C. I'm James Foster here in D.C., and I believe I see Sabina Alkire, Director of OPHI, online, who, as I understand it, has her own presentation and may have to leave a bit early. Hi, Sabina. A big hello also to the good folks gathered in person in Oxford. Hello there. Before proceeding with today's event, I'd like to give a shout out to the key personnel behind the scenes. To Claudia Vidal Cuellar and her colleagues in OPHI, and to Maria Papera and her colleagues in IIEP for putting together such a compelling series and running the show so efficiently. Thank you very much.
Thank you, James.
Well, today I'm especially happy to see our old friends and colleagues, Heriberto, Tapia, and Moumita, Ghorai, from the Human Development Report Office of the UNDP, who've been hard at work on their latest piece using machine learning to estimate multidimensional poverty. Welcome to you both.
Thank you, James.
To be sure, the highly anticipated data revolution needed for evaluating progress with the SDGs has never materialized, and now even long-established series like the DHS would be in jeopardy. Can machine learning and night lights data provide a useful alternative? We're looking very much forward to your answer. So without any more delay, please proceed. Heriberto?
Thank you, James. It's a pleasure to be here with my colleague Moumita. And also I would like to extend my gratitude to Claudia and the team organizing this event. So we have some slides. Just to give you a little bit of context, we are working now on the next Human Development Report on artificial intelligence. So in the report that we think it's going to be launched in around May this year, we are going to be asking how artificial intelligence and new technologies could be used to enhance human development, and that pushes us to look for different aspects of the technologies and uses, and one of them has to do with the work that we do in this group, all of us all the time. So how we can get better estimates of socioeconomic indicators and how we can track the progress in development. Moumita, maybe you can start sharing the screen.
Yeah.
So this is a project. It's an exploration in how we can use satellite images and machine learning in order to estimate multidimensional poverty. This is part of a work that we have been developing with a group of colleagues, Luke Sherman and Solomon Sian from Stanford University, and John Proctor, who is now in the University of British Columbia. So next slide, please. So in this project, what we try to do is to estimate global multidimensional poverty using the definition of the traditional MPI. We will go into that in a moment. And here the data, as you all know, most of the data come from two standardized surveys, the DHS and the mix. And this work has been difficult in part because of the limited availability of data. So in this index that we produce every year between OPHI and HDRO, we typically are able to cover around 110 countries. Last year was 112 countries. But in many cases, the availability of data is not only constrained to some countries, but also in terms of the year of the data, we face big lags. Just to give you an idea, in the report that we produced last year, for 15 countries in the sample, the most recent data was from 2014 or earlier. So, and this is a really big problem because we really don't know very well what is happening in those countries. So here the idea is to use new techniques, new sources of data to see how we can complement the estimates that we produce using the surveys and the traditional methods. Next slide, Moumita, please. So why the use of satellites? Well, first, as I mentioned, this is something that could relax the constraint in the availability of data in terms of countries and also over time. So also satellite data can give us a lot of flexibility in capturing what is happening in every place in the planet, and also has the potential of give us the flexibility of tracking things over time. This is one of the promises and something that we can discuss later. We are not there yet, but it's something that if these technologies work well, we could potentially do. Another good characteristic of the satellite imagery is that it's standardized by construction. So therefore, to the extent that we can construct with models to use this data, we will be able to produce estimates that are comparable across different regions and also scalable. Something very important in this agenda is that now we have the support of new technologies, because these databases are huge, are not that easy to deal with, but new techniques in artificial intelligence and machine learning can help us with the processing of this data. Something very important that I want to stress, that here we have, as in other aspects of the use of artificial intelligence, some potential tensions between augmentation versus replacement. So the key question for us is how satellite data can augment our ability to track multidimensional poverty, given the limitations that we already have. Now, here there are different options in which this augmentation can take place. One is about the prediction of the levels of multidimensional poverty. This is what we are going to be exploring in this paper, but there are other ways in which there could be this complementarity. For instance, a process of downscaling. So given that we know what is happening with the values of a variable at the country level, so then we can disaggregate it. And also there is the use of this technology to track the situation over time. Next slide, Moumita, please. Now, there are big challenges. Some of them have to do with the results themselves that we will explore later. But also there are some issues that are conceptual. So it's been hard to get to this point to talk about a human-centered approach and then use a technology that doesn't seem to be dealing with people, like just taking images and process them through machine learning. So by construction, there are many things that these technologies cannot capture. So it's very important to be clear upfront about the intrinsic limitation, conceptual limitation of the technology. Even if it works well, there is something inherent that this technology is not captured. Also, there are problems with incentives. So we're already having a lot of problems generating the instruments in order to collect good data, which is essential. So depending on how we develop and use these technologies, we might generate the incentives to produce even less high quality data. And so this is something that we also need to consider. There are also potential ethical concerns to the extent that if these methods work well, we can potentially see too much and violate some of the principles of privacy. And also this technology is still very costly. So there are some resources that are freely available, but it is still very complicated. However, the method that we're going to be presenting today, in general, is based on certain set of data and also set of techniques that are not that computational intensive. I think this is one of the benefits. Next slide, please, Moumita. So our approach, as I was saying, is to develop new tools in an experimental way. And we're doing this in different aspects. Also to motivate, I want to share with you some results that we have in a separate paper that is about the Human Development Index. In that paper, what we are describing is a technique of downscaling. So given that we have the value for the HDI at the country level, we can go into different levels of disaggregation. And you can see the power of this. So how we have currently just about 190 data points, and then we have the flexibility by using these techniques to cover every province in the world, every municipality in the world, and also every tile with people in the world. So that increases hugely the availability of data and the potential to understand certain things. So again, the goal is to get complementarity, to understand what works, what doesn't work, and having in mind that the technology will continue to improve. So for us, this is like GPT-2, so where we can understand things, get decent results, but to the extent that we continue, probably we're gonna improve even more over time. So I'm gonna give the floor to my colleague Moumita, who will continue with the presentation.
Thank you, Harry. Thank you for the introduction to our paper. Now, I will start by talking a little bit about the previous literature on this topic. So as we can see, over the past decade or so, there has been an increasing interest in using satellite imagery and machine learning to understand socioeconomic variables. Now, as Harry mentioned, the appeal of this approach is that since we don't have data in a lot of places, we can use satellite imagery to extract that information at a much lower cost compared to a ground level nationally representative or a globally representative survey. For example, if you look at some of the literature, like in the GENE 2016 paper, they used detailed daytime satellite imagery, and they tried to predict poverty indicators at the regional level. And their model kind of explains between 55 to 75% of the variation in the household asset wealth across 5 countries in sub-Saharan Africa. And if you look at a few other papers around that time, they also do similar kind of analysis, like the IIEP 2020 paper that developed another model that also does give very good accurate results, very good results. For example, in that paper, 70% of the variation in wealth management, wealth measurements based on ground data. Now, most of these papers uses deep learning methods like convolutional neural networks that kind of algorithmically can classify objects such as building areas, roads, and crops, and roof types. And over the years, we have seen that there has been an improvement in these methods, and they are kind of good enough, or the predictions are high enough that these models can be used for targeting aid or program evaluations in remote communities where alternative source of information is very difficult to get or unavailable. For example, in one of the papers, Vogel 2024, they evaluate the 2000s roads construction project in India, and they look at whether the investments in road improvement improved welfare in urban markets. Very recently, one of the papers that was published this year, in fact, I think in March or April, this Jung paper, the last one in the slide, that evaluates the distribution of community development aid across Myanmar. And their model can predict over 70% of the aid per capita per community. And this is quite comparable if you look at the literature over the years. The prediction capabilities kind of range between 50 to 70%, and in some cases, even more than that. So the models over the years have become better, and they can predict with quite high accuracy. Now, if we look at, now let me move on to our contribution to this literature. So even though these methods, most of the papers that use the convolutional neural network techniques, these deep learning methods, they produce really good results. However, they still remain inaccessible to a lot of contexts. For example, government agencies or research organizations in low-income settings where they might not have a huge computational power or a large-scale storage for these big high-resolution satellite imagery. And in a lot of cases, government agencies and local organizations might be forbidden even to access such high-resolution satellite imageries. And so in our paper, what we do is we use this another source of data, another model that is called mosaics, and I will talk more about this and how this method was generated and how data is extracted from it. But this is a very flexible, scalable approach and requires comparatively less computational power, and a person with very limited knowledge about GIS or the technicalities of extracting data from satellite imagery can very easily use this data and run linear regression models very easily by merging them with other sources of data. So one of the papers that uses this mosaics model to estimate human development index, the paper that Harry just talked about, uses similar models and found their performance accuracy to be around 50 to 75%. Now, for our paper, we use 3 types of data. We use daylight satellite imagery, daytime satellite imagery, nighttime satellite imagery, and we also use demographic and health survey data. Now, this tool, Mosaics, was introduced by Rolf in their 2021 paper, which is a generalized feature extraction program that allows users to extract information from satellite images. So what it does is that it takes small patches of a bigger satellite image and uses as a filter to scan across the larger satellite image. And through the scanning process, it can detect patterns like buildings, roads, and vegetation, housing. And then these results are adjusted using a nonlinear transformation. And then these nonlinear transformations are then aggregated into a single number. So basically what we end up having is this a vector of features for each geographical polygon, and end up having a matrix with rows and columns that is very easy to use. So in this paper, we've used 4,000 features like that, and each feature basically describes the similarity between the satellite image and that smaller patch of imagery that was used to create that feature. So together, these mosaics features form a basis that can be used to describe the complex and rich structure within that large imagery. And other data sets can be merged and linked with it, and simple linear regressions can be run, and we can use that for predictions. We have accessed this data from www.mosaics.org. Here in this website, we can put in the latitude, longitude, geographical regions, and we can just get the extracted data in a tabular form. Now, why we are using mosaics features? Because the Rolf paper and the other literature shows that the accuracy achieved from these mosaics features were quite comparable with the other deep neural network models used in other papers, but with lower computational capacity and can be scaled globally. And these features have proven highly effective in predicting problems, including forest cover, population, elevation, housing prices, and simply by using linear models and satellite imagery alone. And this ability of the features to predict socioeconomic data using such simple techniques and much less computational power makes it very appealing for our research. So these features is like one-time generation, can be generated once, which is already being generated in the data source that I shared, and can be shared to literally every researcher out there who is interested. So to supplement the daytime satellite imagery, we also use nighttime light data. And the data is collected from the Defense Meteorological Satellite Program. And we specifically use the annual composite for the year 2013, which was kind of the last year the composites are available for. And this data is actually the luminosity data that ranges from 0 to 63. The values ranges from 0 to 63. But we do not create the random convolutional features from the nightlight data, because the pixels of the nightlight data are quite large. And so we use a binned method. What we do is split the luminosity data into 20 categories, one group for 0 brightness and 19 other groups for brightness level that spans between 0 to 63. And this approach allows nightlight to associate non-linearly with the outcome variables, because it is quite well established in the literature that the nightlight intensity is not linearly related to socioeconomic or economic activity or development. The changes in brightness do not correspond to proportional changes in economic activity. In addition to the satellite imagery, we also use DHS data. On the right-hand side of the slide, as you can see, I've produced a global map where the red or pink areas are all the countries that are in the MPI that have the MPI data that we produce and we launch every year together with OPHI and HDRO. And the blue areas are where we have the DHS data with geolocation, because that will help us to merge it with the satellite data and do our analysis. So for this study, we use 3 dependent variables. 2 of them are multidimensionally, comes from the Multidimensional Poverty Index analysis, which are weighted deprivation score and percentage of multidimensionally poor people. And another is income proxy. So to give like a brief overview of the variables, so as you can see on the left side, we have the structure of the global multidimensional poverty, and we use the global method. So the MPI has 10 indicators, and they are grouped into 3 dimensions: health, education, and living standards. Health includes nutrition and child mortality. Education includes years of schooling, school attendance, and living standards includes cooking fuel, sanitation, drinking water, electricity, housing, and assets. So now each indicator has a threshold that defines whether someone is considered deprived or not. For example, if a household doesn't have access to clean water, or if a household doesn't have, household doesn't have access to electricity, and so on. Now, all the indicators in the global MPI are weighted equally. So as a result, the health and education indicators are weighted 1/6 each, and standard of living indicators are weighted 1/18 each. Now, after weighting, we calculate sum of the weighted deprivations, and if the global MPI identifies people as multidimensionally poor if the deprivation score is 1/3 or higher. So in this analysis, we use that sum of weighted score, and we also use the percentage of MPI poor people, multidimensionally poor people in each DHS cluster. We also use, for comparison, we also use another variable, which is the income variable. And since household service DHS does not report income of individuals, what we do is we proxy the income variable using a simulation. So we follow a Harton Klassen paper from 2010 that proposes a method to estimate household income per capita using asset indices. So to do this, we use the DHS Wealth Index, and we assume that the distribution of the wealth index is same as a modeled income distribution that we create using a country-specific data on income per capita and Gini coefficient for each country. And from there, we extract income for each household. So using this data, we train the models using 5-fold cross-validation with ridge regression at the cluster level. And this is the linear model that we estimate. And ridge regressions are used in case of when there are too many predictors. And since we have 4,000 mosaics, columns, and 29 light, we use regression to prevent overfitting. And to estimate this model, we split the data into 80% training set and 20% test set. So we keep the 20% test set aside, and within that 80% training data, we use it for cross-validation, and a 5-fold cross-validation technique is used to determine the penalty term for the ridge regression, basically. That 80% of the training data is divided into 5 folds, and out of which the 4 folds are trained and tested on the rest of the and the 5th fold. And this technique is repeated 5 times. That allows the model to be trained and tested on different portions of the data so that we get the optimum penalty term to include it in the regression. And in addition to a 5-fold cross-validation where the division is done randomly, we also use a country-fold cross-validation method where the data is grouped by country. So in our models, we have 4,000 mosaics features, which are the daytime imagery features, and 20 nighttime imagery features. And for every model, we either use all of 4,020 features and compare it with only 4,000 features and only 20 nighttime features. All Y variables, which are the weighted deprivation score, percentage of multidimensionally poor, and the proxy income variable, are estimated using both a full variation model and a within country variation model. And all the models are trained at cluster level. Cluster is the DHS cluster, which is basically a group of few households, which is equivalent to a neighborhood or a village. For measuring the performance of the model, we use 2 commonly used metrics in the machine learning literature. We use the coefficient of determination, which describes the accuracy of the model, basically. It explains the variability in the data. Closer to 1, it explains more and a better model. If it's 0, or it also can be negative, that means it does not explain much. And the other matrix that we use is the square of correlation coefficient between the observed and the predicted outcomes. It quantifies how closely the predicted values align with the observed values. And while both of these are quite similar, and R-square basically evaluates how much the variation in the Y variable is explained by the model, and rho square directly quantifies the relationship between the predicted and observed value. And we also estimate both the full variation model, which basically describes how well we estimate poverty when we use all the information. And for within country performance, and we also estimate within country performances, because in the full variation model where we get the across country performance, it ignores the local level variations. And to understand the variation at a local level, we take out the country specific factors. To do that, we subtract country averages from each variable. For example, and we do that for each variable and at the cluster level. In summary, we can say that full variation performance looks at overall predictive power of the model across all data and whatever information we have available, while within country performance kind of isolates and evaluates the model's effectiveness, capturing at a more local level, a localized poverty variations. So now we can look at the results. So this is the first model where deprivation score, proportion of poor, and income proxy is predicted. And the first row of images show the full variation model, and the second shows the within country variation. As we can clearly see that the full variation model, since we are looking at across country performance, does give a better better prediction. In case of deprivation score, our model predicts almost 70% of the variation in the weighted deprivation score when we're using both mosaics and Nile light, which is total 4,020 columns. And in case of proportion of multidimensionally poor people, we see that our model can predict almost 65% of the variation. And in case of income, our model can predict 69% of the total variation in the proxy income variable that we created. In case of within country variation, we see that our model predicts around 52% of the within country variation in the deprivation score, and 47% in the proportion of multidimensionally poor, and 61% in the income proxy variable. And we also, I don't have the results on this slide right now, but we also estimated the same models using only mosaics and only Nile light. And we found that together, mosaics and Nile light, together the daytime satellite imagery and nighttime satellite imagery performs the best compared to only Nile light or only mosaics. And mosaics does better than only Nile light. We also did the same analysis for all the indicators of multidimensional poverty index. And as kind of expected, as you can see that the standard of living indicators, for example, electricity, drinking water, sanitation, housing, cooking fuel, they do comparatively better than other indicators, like health indicators, specifically like child mortality and nutrition. Because here we are looking at a satellite image, and obviously the things that are more visible in a satellite image will be easier to predict. For example, in case of electricity, we see that our model, the full variation model, predicts 70% of the total variation using the mosaics plus Nile light model. And In case of within country, when we are taking out the country effects, our model predicts 43%, 42% of the variation in deprivation in electricity. So, and in case of child mortality and nutrition, we see that the model does quite poorly, which is expected because it's difficult to visualize. It's not possible directly to visualize some of these indicators. And this is one of the things that Harry talked about in the beginning of the presentation, because it will be difficult to predict things that are not visible directly in a satellite image. In case of housing, we see 59% of the variation is explained by our model, and 53% in case of a within country. 53% within country variation is explained by the model. In case of cooking fuel, we also get quite good accuracy with 67% variation explained by the model, and 55% within country variation explained by the model. We further extend this analysis by splitting the data into urban and rural, and we try to see how our model does in urban settings and rural settings. We see that in rural areas, the predictions are better. And this is I'm only showing the full variation models. We have run the within country variation models as well, and the prediction accuracies, obviously, for the performance will be a little low when we're taking out the country specific effects, but they're pretty comparable with the total overall model. And in case of here, we see that in case of rural areas, we see that there is the model performs better. Around 70% of the variation is explained by the model in case of the rural deprivation score, and 65% of the variation is explained variation in the proportion of multidimensionally poor people variable, and 66% is explained by 66% of the variation in the income variable is explained by the model. Whereas in urban areas, it's still the performance is okay, but it's not, it is much lower than the rural counterparts. For example, in urban areas, the performance is around 55% for deprivation score, and for urban proportion to multidimensionally poor people is around 44%. And in case of the proxied income, the accuracy is around 54%. And for all these analysis, we have done also the only mosaics and only 9-line models. And for every case, it is pretty consistent across all the models we have run. The mosaics plus nightlight model performs very good. Nightlight specifically performs very good for income variable. But even then, if we include the mosaics model, the mosaics features, the performance improves significantly. Now, lastly, I would like to share, we have also estimated the same model at the subnational level, which is another interesting feature of this mosaics model, that we can simply add features at different administrative level, and we can scale up and scale down accordingly. So here, what we have done is we aggregated over subnational level, because we have subnational level MPI data, and at the subnational level, which is the admin 1 level, we have run the same models, and what we can see, again, the mosaics plus 9-line model performs the best among all 3 models. And in the full variation specification, we see that around 72% of the variation is explained by the mosaics plus 9-line model, and around 49% of the variation, within country variation, is explained by our model. So to conclude, I would like to say that since there is a lack of updated household survey data that is required to estimate MPI and other socioeconomic indicators, we find that our model, using satellite imagery, daytime and nightlight satellite imagery, are performing quite good, which is comparable, and the results are quite comparable with the existing literature. And we see that the models have quite high accuracy while predicting the MPI indicators like the deprivation score and percentage of poor, multidimensionally poor people. And in fact, it also quite efficiently predicts the proxy income variations. And the results show that there are differences in terms of predicting in rural and urban areas. And the models do perform better while predicting the standard of living indicators among the MPI, the multidimensional poverty index indicators. However, I would like to say that there is a limit to how well the satellite imagery can be used to predict. And survey data is also equally important. So this cannot replace a good quality survey data that is needed to train these data sets, and so that we can use that trained model to predict where we don't have data. And therefore, survey data and other data sources remain equally important. As next steps, we plan to measure and estimate these poverty measures where we don't have the data. Right now, we are still testing and training the data. And by estimating, we can help target social programs in data poor areas. And not only across regions, we also plan to estimate these measures across time as well, so that we can have we can track improvements in socioeconomic indicators across time. Okay, thank you. That's all from me. And I would like to welcome any questions if you have.
Right. Well, we have about 11 minutes for questions. I have a number of them. I'll start on the chat if that's all right. And then tell me if there are folks in OPHI that would like to chime in. The first comment just said, could you send some files and codes? And you can go ahead and address that directly. And then the second is, what are the main reasons for better predictions in rural areas? Are there less variables to analyze? I guess, Heriberto, you're already providing the answer. You could also just tell it to all of us as well. And then finally, we have a question. Thanks a lot for the presentation. Really interested in important work. Could you expand a bit on the higher variation in the errors for predicting the share of multidimensionally poor compared to the deprivation scores? Shouldn't they be similar? Also, could you expand a bit on the ethical considerations around those errors and model fit? So I'll stop there and turn it over to you all to respond.
Okay, so yes, I could, to answer Daphne's question, yes, I could share codes and files. Yeah, and I just don't know where to share, but yeah, I could. If you can share your email, I can share the link.
We can share the email if it's all right with you, Delphine.
Okay.
Okay, great. And the second.
So in terms of the different performance in rural and urban, we are still trying to understand. But something that might be happening is that in some rural areas, there is more variation, right? Most of the people that are multidimensionally poor are in rural areas. And therefore, it might be the case that these fluctuations in socioeconomic conditions, because are stronger, are easier to see using satellite data. But this is still something that we need to explore further. Yeah, I don't know, Moumita, if you have any insight on that.
Yeah, similar answers, because the whole MPI measure, the questions are kind of biased towards rural poverty, the questions that we consider. So that can be one of the reasons that we see that. Yeah, and the second question was also, could you explain a bit on the ethical considerations around these models?
But there is one question that Tobias is asking. It's about the differences in predicting the prevention score versus the headcount. My interpretation here is that in one case we have a linear variable, right? So a continuous variable. In the other, we have a variable that is discontinuous. It's not continuous. And we are using a linear model in order to predict this. So my conjecture is that in terms of the explainability, the model is better positioned to explain a continuous variable. So probably, and this could be something that we could do, is to use a classification technique in order to try to predict the headcount ratio, whether people are poor or not poor. So that could be maybe something that we can try in order to address this. So maybe it might be the case that the selection of the model it works just better with one of the variables than the other. In terms of the ethical considerations, there are many things, right? So I mentioned before the issue of the possibility of really identify people using these models, and also some information from, even if it is anonymized, from the perspective of the household survey. If we identify things using satellite, we can pin down who is who. But the other big ethical consideration here is when we are ready to use this. Because no matter what, we press enter and we get a result. And which is very tempting, right, to then use this. And I think we're still struggling to find the balance. So, because something is better than nothing. However, we still don't have a lot of clarity what is good enough. So in that sense, your inputs could be very important for us.
Right. So how about an OPHI proper? Anyone have questions in the audience?
Yes, we have a couple of questions. Yes.
Did you notice any differences between different types of countries, or countries that had more or less like the data collected on the ground? Did you notice poorer or stronger correlations of the different countries?
How about it, folks?
Yeah, Moumita, maybe you can answer, but yes, there are differences of when we treat different countries. We are still trying to understand that there in certain countries, when we split the sample using whole countries, the results are just not very good. Maybe Moumita, you can say something about this. And yeah, and maybe the geography of the country might be conspiring against a good identification of the socioeconomic conditions. Over to you, Moumita.
Yes, so we did, like, for example, in this presentation, we mostly showed the five-fold cross-validation regression models, where the five-fold was based on, it was randomly divided into 5 parts. But we also did a country-fold model where the whole data set was divided into 5 parts based on countries. And we saw that in cases where Asian countries, if we train the data on Asian countries, for example, DHS, the India data set is huge. And when you split the data, that goes into the training set. If the majority of the country from sub-Saharan Africa are in the test set, the performance is not very good, depending on predictions. But trained on sub-Saharan Africa, and if the test set is also sub-Saharan Africa, then the prediction is much better. So there are little nuances like that that we still need to work on and think a bit more about why this is happening and how this data set can be split and what other model specifications can be used.
Another one?
Yes, we have, yes.
Hi, thank you for the talk. I was wondering why, in particular, you chose a linear model, and that's kind of assuming that the indicators is dependent on a linear combination of your satellite features. And I also wonder if you expect that relation to change depending on like the culture or the geographical location that you're looking at.
Yeah, so the selection of the model is something that we are very flexible about. So for this exercise, we try to homogenize the analysis to one type of model, precisely to learn. But we are exploring this project in order with other techniques, in particular classification techniques like XGBoost, which is I think very, very powerful in order to deal with classification. So about the culture, this is precisely the type of component that we cannot capture. And the thing is that even if we capture it well statistically, I think this is a valid question for us and for the use of these techniques.
Another one?
I think we are all the same.
Fantastic. Then I'll just finish it up here. One of the main problems, of course, with using night lights and other data of this sort is envisioning the pathway as to how policy might actually be implemented and therefore change the variable itself that you're observing and therefore lead to a conclusion that poverty is actually down. So I'm much more interested in the over time estimate because, you know, there are aspects of the level estimates that are not that interesting. So over time, as a guide to policy, what do you see? What are the problems and what are the possibilities? And that'll be the last one for today, except there are a couple of smaller ones that could be responded to in person. If you would do that, that would be great as well before we leave.
Very good. So I just see a lot of interest in engaging in this type of work. So please, I think Moumita, you can publish your email address, please, or mine. You can get in touch with us, and because this is a journey, this is going to continue to grow, and I think we need to keep learning together.
Thank you much. Okay, anyone else before we go away? Otherwise, I'll say that's it. Moumita, could you put up your email address somehow? I'm not sure if we can handle that at this point, but let's try.
I can put it in the chat.
Yes, please do that. And in fact, I'll occupy time right now while we wait for the chat to show your.
Oh, sorry.
You need to put
mine is Heriberto.tapia, like my name.
Ah, okay. Send it to Heriberto.
UNDP.org. So, and Moumita, I think it's put in here email address in the chat.
Okay,
it's
folks.
Moumita.Ghorai@UNDP.org.
Okay, so that should be clear for all of us. And so for those of you who would like to get more information, please contact them directly. Otherwise, you can always contact me. My email is everywhere, jamesfoster@GW. That's it for right now. To those of you in Oxford, have a wonderful rest of the day. I see it's still beautiful outdoors, so I will have a great day, and I hope you do too in New York. Take care. Thank you so much.
Thank you.
Thank you, everyone.
Bye-bye
Bye.
now.
Bye.
Bye-bye.